Hello, welcome for Start Here for Space. My name is Rachel McNeal. I'm a government relations manager for Maxar Technologies. Today, I'm going to talk about all things on orbit servicing, assembly, and manufacturing. We'll be talking about mission applications, the history in the US of this capability set, some of the programs that are happening here now and into the future, and what this means for space overall. I'll close out with a talk about policy and regulatory issues. So to start out, did you know that satellites aren't currently made today to be serviced or refueled? So think about it. You buy a car, and we're talking about space, so a really expensive car. And you know that at the end of its life, one gas tank, that car will no longer be operational, and you'll actually just leave that car on the side of the road. So this is, for all intents and purposes, what we do right now with satellites and spacecraft. We have over 4,000 operational satellites on orbit today. 1,200 were just launched this last year. And you can see on this slide all the objects that are around our Earth. So when you think about this approach, it really isn't sustainable long-term, which is why OSAM is so important. Diving into this next slide, we really want to set the definitions and what we're talking about today. So when we're looking at OSAM, which I will refer to it throughout the presentation, I'm talking about on-orbit servicing, assembly, and manufacturing. So servicing is everything that comes with fixing or changing a satellite. That could be refueling, that could be changing out the purpose or mission through changing payloads. And that could be something like providing support for the ability to move or maneuver in space. When I talk manufacturing and assembly, as it's stated, it's really the idea of building or creating something new. Let's jump right into mission applications. So at the beginning of this episode, we actually talked about life extension. This is the idea of refueling a satellite. It can also be something like providing maneuverability to a satellite that no longer has that capability. Another mission area is inspection. So if we expect something might be wrong with our satellite, there could be a spacecraft where we put sensors on that spacecraft to approach the satellite, take images of the satellite, send that back to Earth, and then analyze those and diagnose any issues that's going on with that spacecraft. Next, we could talk about repair. So satellites oftentimes can have technical issues. They can have issues during launch. There can be unexpected problems or anomalies that come up in space, which leave them non-operational. And so as a result of that, the ability to repair a satellite, so to fix the problem and allow it to continue its mission, can further go towards that idea of sustainability in space. I'll talk about updating payloads now. So as we innovate, our technology is moving faster than ever. Right now, we build the requirements or the set of specifications for a program going or at the beginning of its life. And so we set those specifications, which could be years, possibly even a decade or decades before that spacecraft or satellite launches. And then while it's in space, we would have the ability with something like OSAM to actually change and update that spacecraft with possibly new payloads, so new missions. So maybe it's a weather satellite and we add on something for remote sensing that allows us to take images and look at Earth. And so this adaptability, again, plays into the importance of OSAM and where it supports our mission. Going on to the next one is debris removal. So we saw that picture early on of debris in space. It's a congested place, and we are only launching more and more satellites year after year. And so the ability to take a satellite that's no longer operational and move it out of the orbit where operational satellites are can help us reduce the risks and keep our satellites safe and operational in those spaces. And so you could actually have a spacecraft that has the OSAM capabilities to grab that spacecraft and move it to another orbit, like something like what we call a graveyard orbit, which is an area where there are not a lot of operational satellites. And so it won't impact or cause any harm to other satellites. Next, we'll talk about manufacturing and assembly. These capabilities are truly transformative. We think of architectures today based on what we're doing on Earth. We build these architectures on Earth. And it really is a transition with this capability to think about building architectures in space. So not only is it the ability to possibly build a satellite in space or a spacecraft or maybe a future station, But it's also the ability to ensure that you don't have to put spacecraft through the risk environment that launch requires. So when you launch a satellite, it's actually the most hostile environment that satellite will go through, or that spacecraft. And so as a result of reducing that risk and building that in space, you won't have to build to that environment, and you won't have to risk there being an issue with the satellite once it gets to space due to anything from the launch. In addition to that, we build right now to fit on the top of a rocket. And that space on the top of a rocket is what we have to fit our spacecraft and satellites into. So our biggest telescope here that NASA is building today is actually being furled up and curled to fit in that fairing at the top of the rocket, because it was built to a size that would give us a capability that was necessary to really see to the beginning of time. And so as a result of that, if you think about something, for example, like a telescope, if our future telescopes were able to be built in space, they wouldn't be confined to the area on the top of a rocket. So the capability that could come out of that could be exponential, being that there was no parameters around how big that spacecraft or that telescope in this example could be. All right, with an idea of what OSAM capabilities can provide, I would like to talk about next the history of satellite servicing and building in the United States. So looking at you can see this slide shows a whole history of some of the major moments and points that really contribute to the story behind these capabilities.
Skylab had some issues upon launch, which caused it to lose a portion of the external shielding, which meant the temperature inside Skylab was uninhabitable for humans. A crewed mission was able to successfully install a shield, which corrected the temperature and enabled astronauts to live and work in space for the first time. The SolarMax spacecraft was designed to investigate solar flares and other phenomena. The SolarMax encountered an attitude control issue in space, which caused it to lose stability. As a result, a crewed mission with astronauts was sent up into space and was able to successfully fix the spacecraft.
Hubble is the next telescope that we're going to talk about today. So Hubble actually had 5 crewed servicing missions. And so what I mean by crewed is astronauts actually going to fix the problem. And so Hubble, on the first mission, its imaging payload, which takes the image of the Earth, was actually blurred. And so as a result of that blurring, was not able to take clear pictures into space as they had hoped. But through the servicing by the astronauts, they were successful in fixing the problem. And so those are the images we see today, and some of the images that really sparked my passion for space and thinking what was beyond Earth. In addition to that, they had 4 follow-on crewed missions to continue to service Hubble in the decades or in the years that you can see listed on here. Next, and this was really a revolutionary time, but we were talking about the International Space Station again. They performed robotic refueling missions. So instead of having astronauts, they actually did it through robotics.
Mission Extension Vehicle, also known as MEV, performed 2 successful missions where it docked with a communication satellite in geosynchronous orbit, taking over what is called station keeping. MEV uses its own fuel to maintain attachment and provide capabilities such as attitude control, so for stability in orbital positioning and maneuvering. MEV successfully performed the ability to extend the life of a satellite not made to be serviced.
And the last one I'll mention today was just here recently, the ELSAD, which was launched and is going to demonstrate the ability to remove debris. So talking back to the congestion we see in space, a really important capability. So diving into the future and where we're going, when we talk about OSAM, we saw in the history of the United States, we've worked on these different aspects of these capabilities. So the on-orbit servicing, assembly, and manufacturing 1 mission, which NASA is doing in partnership with commercial industry, is a great showcase of the ability to put all of these capabilities in one place. So the mission is actually going to put together or assemble a 9-meter antenna in space. And then in addition to that, it's going to 3D print a 30-foot beam. And then the last thing is refuel a government-owned satellite in low Earth orbit, really combining the full suite of these capabilities. And it's been dubbed the one-stop service shop. So back to my car analogy, but you think about taking your car to the shop. Well, in this case, it's the service shop in space. So you can do everything from refueling to tune-up to payload shifting to building something entirely new. So I'm going to go ahead and play a video for you here that you're hopefully able to see and really see these capabilities demonstrated in space.
Upon completing the servicing mission, Maxar's Space Infrastructure Dexterous Robot Program, or SPIDER, will demonstrate the on-orbit assembly of a multi-panel antenna reflector and testing to confirm operational status. Next, SPIDER will demonstrate on-orbit manufacturing and assembly using Tethers Unlimited's MakerSat. MakerSat will produce a 10 to 20 meter beam. SPIDER will disconnect MakerSat with the beam and reconnect it physically and electronically to the spacecraft for testing.
It's always fascinating or blows me away to actually see it in person. It's one thing to talk about it, it's one thing to actually visualize and see this. So I just want to illustrate that this important partnership and really the future where we're going is a way to invest in capabilities like robotics. You saw those robotics arms on there, which are going to be critical to OSAM. 3D printing, which is an important part of this additive manufacturing or the ability to build in space. And then the last thing, which is rendezvous and proximity operations. RPO is what it's called sometimes. And it's basically the idea of aligning and connecting in space, which you can imagine is very tricky when satellites, particularly in certain orbits, are continuing to orbit around the Earth and you're trying to connect with to perform your mission. So that's a very critical technology for this industry and really the future of these capabilities. So as part of this greater OSAM program that NASA is doing, they're performing a mission here as early as 2022. Well, they'll be sending up a spacecraft to perform 3D printing, and they're actually going to 3D print two 33-foot beams, again demonstrating these these technologies in space. And just to close out on this, the really critical part is it really is a partnership between all. This is a new market space that industry is innovating in, that government like NASA and national security are working within to address entirely new missions. And so this critical time of developing these technologies is going to feed forward to a time and space when we have, as I vision it, servicers all over being able to build kind of these future architectures that we talked about in space. All right, I want to bring this all together. Why does this matter for space overall? So you can see here a few keywords on the slides that you'll hear often, I'm sure, and have heard before in the space industry. And really how OSAM plays into this is the idea of sustainability is about us being in space for the long term, for continuing to grow, to continuing to build architectures and opportunities. And so doing this, OSAM actually allows us to do it for a lower cost. So right now, to put a satellite in space or a spacecraft, it can be millions of dollars, hundreds of millions of dollars, or even billions of dollars to do so. So to reduce that cost will have really big impacts on the ability to lower the threshold for access to space. And if more people and organizations can access space, we can bring greater ideas to solve some of the greatest challenges in space that impact back here to Earth, but also to continue to grow what we're doing there, from increased architectures or access for humans to do research, robotics to do research, to perform in critical missions like communications or GPS, or as I think about it, our exploration here as we're going back to the moon and onto Mars. And this is a really important part of that being the future of only growth in space. Next is adaptability. So the idea that OSAM could actually go in and change a system. So where technology is moving faster and faster. And when I say that in space, it used to take really years, maybe even decades before that, to build something and put it in space. And now we're getting to a place where years is more normal, and even months we're getting to where that's the timeline to access and get to space. And so as that timeline shrinks and as there's less time from the time you build a spacecraft or satellite, you put it into orbit, And now we have these new technologies, advanced payloads. We have new missions that need to be addressed. The ability to adapt with OSAM to add on to a current or existing spacecraft will allow us to keep up with the pace of innovation. And the last thing is resiliency. So I think about this, but I've heard it said many times. What would you do with a day without space? And so in thinking about that, I think about I wake up in the morning and I look at the news. That uses space. I get in my car and I turn on my GPS. That uses space. And then finally, I'm going to grab a coffee and I'm paying for that with my credit card. And again, that uses space. And so there's all these critical capabilities that keep humanity connected and operational and economies going. And so the ability to have something like OSAM, which allows us to have more resiliency or to ensure those capabilities can continue to perform is very important. So with all of this said, and recognizing that OSAM is a critical capability, what do we do around policy and regulatory environments? And what can you do to get involved? So I just wanted to talk through a few different policies and issues that are impacting OSAM and list and identify how they play into the future of this capability. So when we look at things like first, space situational awareness and space traffic management. So you saw that first slide that showed space debris. Well, it's really critical to have an idea of where each of those objects are, so to track those objects, and then have a way to, as space traffic management says, manage those objects, just much like what we do with the airspace here on Earth, to make sure that airplanes don't collide with other airplanes. And so as we get more congested, there's more risk in debris hitting other satellites, satellites hitting other satellites, spacecraft running into satellites. And so the ability to manage this is going to be important for space overall, and particularly for OSAM. So if I have a spacecraft that's going to perform an OSAM mission and it needs to approach another satellite, it's going to be critical that that satellite or spacecraft can find that satellite safely, so not to impact any other things operating or moving in space. And then in addition to that, to be able to perform the mission and remove itself from the mission successfully without any issues occurring. So that's going to be a key enabler. So the next one is going to be norms of behavior in space. And so this is the idea that as operators, whether it's academia, industry, government, operates in space, there has to be a standard across where we understand other operators' actions. And so this is a really international collaboration because space is an international place. And with that said, it really applies to OSAM because one thing that OSAM spacecraft would be doing is they would actually be approaching other spacecrafts and satellites. And so those operators need to know that they're doing so, first of all, with goodwill to perform the mission they're tasked to. And so they're not, and to clearly know that they're not doing it for a nefarious purpose or a purpose that would be harmful to the satellite. So really underpinning this all is transparency. It could be anything from reporting that you're operating in that space and that you're going to perform this mission on the satellite and reporting that in advance, to indications and warnings that provide lights on the spacecraft to show that they are performing a mission safely. But those will be really, really critical to the operations of OSAM. So the next thing we'll talk about is evolving interface and safety standards. So when we're talking about this, it's really specific to OSAM capabilities. So I talked about this technology, rendezvous, proximity, and operations, so RPO. And so RPO technology is your ability for one spacecraft to connect with a satellite or another spacecraft. And as I mentioned in the beginning, right now, satellites are not made to be serviced. And so as a result of that, going back to my car analogy, when you fuel your car, you're going to take off the gas cap and you're going to refuel it. In space right now, you don't have the option to take off a gas tank. So it's really standardizing that. Maybe there's one set or multiple sets of how to how to create the actual hardware to have a gas cap on your satellite, or it's something related to docking and actual hardware that'll interface and be interoperable with the other spacecraft. Now, the really important part of this is a growing, evolving industry with new technologies. So there's going to be new ideas that continue over the next decades. And so that's really the key point around evolving, continuing to capture these best practices by industry and sharing those transparently for others to prepare and create and build their future satellites and spacecraft. So the last thing I'm going to talk to you about is regulations. So Article 6 of the Outer Space Treaty requires that whatever country licenses a satellite or spacecraft maintains responsibility of that satellite or spacecraft while it is in space during the operations and afterlife. And so a part of that is that OSAM satellites and spacecraft will have to be licensed appropriately to be able to perform these missions. And so there have been regulations here in the past on other issues, including one recently with the FCC last year, which included or commented on OSAM type capabilities. But going forward, really the question is what agency will be responsible for licensing this type of technology? And that stable framework that's streamlined and grows and moves and is fast with industry is going to be an important part of the future operations of these capabilities. Thank you so much for joining us for the Start Here for Space series on orbit servicing, assembly, and manufacturing. I greatly appreciate your participation and everyone's efforts to make this episode happen. I hope this information is helpful, and if you would like additional information, please look below in the resources. Thanks again for joining us.